Alright, this video is a review for the Organic Chemistry Lab final. We're going to cover four main topics: reactions, calculations, techniques, and then finish with spectroscopy and chromatography. Another reaction we performed was the Wittig. This is the one that you did in class, although you may have had either the methyl or the methoxy benzaldehyde. And we do get both the E and the Z, so I'm showing here the E or trans isomer. Of course, we also had cis, and we get a byproduct of triphenylphosphine oxide. Again, you should be able to do this reaction for not just this specific pair of reactants, but if you get a different pair of reactants, you should again be able to predict the product of a Wittig reaction. So for example, if you're given this methoxymethylene phosphorylidene and the isoamyl aldehyde, you should be able to predict the product. So if we consider what was occurring here, we can think of this as being an anion. We can look at this resonance structure where we have it written as a zwitterion. That makes it evident that this is nucleophilic carbon. That adds to that carbonyl. And so we're forming a carbon-carbon bond between that carbon attached to the phosphorus and the carbonyl. And it does form a double bond, and when it cleaves, of course, the oxygen and the phosphorus bond to each other, and we get the triphenylphosphine oxide as a byproduct. Same thing here. We would be forming a bond between these two carbons, and specifically we would get a double bond. And so we would get these isomeric products, the E and the Z, or the trans and cis if you prefer. And of course we also get triphenylphosphine oxide as a byproduct. But again, you should be able to predict the products for related reactions. And you should be able to explain what was going on during the reaction, why we used the conditions we did, or why we used the workup we did. So how did we separate the triphenylphosphine oxide from the alkenes? Or what was the purpose of using a 50-50 alcohol-water mix for our extraction? These two questions are, of course, flip sides of the same question. We used a 50-50 alcohol-water mix because our triphenylphosphine oxide dissolves in that, our alkenes do not. The alkenes dissolved in the hexane. So the answer to the first question is basically the second one. How was the triphenylphosphine oxide separated? We did a wash with 50-50 alcohol water. Or flip side, why was the 50-50 alcohol water mix used? It was used specifically to remove the triphenylphosphine oxide. But again, you should be able to answer questions like these. You should have an understanding of why you did the workup you did. We gave you a Wittig product. You should be able to take that Wittig product. So you should be able to take this product and determine what would be our starting materials if we did a Wittig reaction, or if we were to obtain this through a Wittig. And again, remember, a Wittig is forming a carbon-carbon bond, specifically in this case the double bond. And it is the reaction between a carbonyl and a phosphonium, or actually the ylide, that forms after deprotonation of the phosphonium salt. And again, we could do this in one of two ways. I'm going to just abbreviate that phenyl. So we could have this as our carbonyl. Then the other side, we would have our phosphonium salt. Alternatively, we could go the other direction as well, where we have our phosphonium salt on this side, in which case our carbonyl would have been here. So either one of these would give the product shown, but you should be able to take the product and work backwards and determine what your starting materials would be given the type of reaction. And of course, to make the ylid itself, you would need to recognize that this would be derived from the corresponding salt, meaning we have a single bond there. And of course we have a proton on this, and we would treat that with some kind of base, sodium hydroxide or potassium hydroxide, to remove this hydrogen. That gives the ylid, which then reacts with the carbonyl. And likewise, if we ask you how we made this, you should be able to determine, well, that would have been made as we did with our phosphonium salt that we made from the alkyl halide. So this would have been a bromide there, and the reactant then would have been triphenylphosphine. So these are all reactions we did. You'll probably be seeing these on the final exam. Not the specific ones, meaning not the same reactants and the same product, but they will be the same reactions. We're not going to ask you about reactions that you did not see in lab, but we will probably change the reactants and or the products and expect you to be able to go forwards or backwards with these reactions. We also did the Grignard reaction. Here we had two reactions that we performed. The first was the formation of the actual Grignard. Keep in mind this is magnesium metal, so there is no charge on it. We did not use a magnesium salt. It is not magnesium ion. Recall this reaction is exothermic, and the sign that you were actually forming the Grignard reagent was the fact that the solution boiled on its own. It generated enough heat to reflux without any added heat. Once the alkyl or magnesium bromide was made, you then did the reaction. We did use 2-bromopropane instead of 2-bromobutane, and again you may have had a substituted aldehyde. But again, these react. We form a new carbon-carbon bond, and initially we form the alkoxide, and we only get the alcohol after acidification. Keep in mind these are separate steps. Shown here a slightly different alkyl bromide that we started with, so we have a different Grignard reagent, and we get a different product. Again, you should be able to do the reaction and show the products for a related Grignard. It may not be a benzaldehyde, it could be a different one. It may not be 2-bromopropane, it may be a different one, but you should be able to draw those products. Next reaction we'll look at is Aldol. Keep in mind again what's going on. The base is removing one of these hydrogens. In the process, we end up forming a bond to that carbonyl carbon. We will get an alcohol from that, but it does eliminate under the reaction conditions to give a double bond. And so we end up with a double bond. Of course, it happens a second time. We do have another hydrogen here. This one can also get deprotonated, and again, we get a second reaction at the second carbonyl, and we form the other double bond. So keep that in mind. Remember that, again, we can ask for the products of a related reaction, and you should be able to do the same thing. Base is going to remove one of those hydrogens, and we end up forming a bond to that carbon. And while we initially get an alcohol from that, it does dehydrate, giving us the alkene. And we end up with this. But just as with the dibenzyl ketone and the benzyl, in this case we have two reaction sites. This carbon also has hydrogens. Again, it can do the same type of reaction, and in fact it occurs a second time, and so we end up with the two alkenes because we have two carbons that are both capable of doing an Aldol reaction. And when we do form the alkenes, in this case, as with the Wittig, it is possible that we can get both E and Z isomers, or both cis and trans. So keep that in mind. Something to think about is how would you distinguish between the two, or determine, giving a nuclear magnetic resonance spectrum, how would you determine whether you have cis or trans products, or maybe cis and trans. And the final reaction you did was the Diels-Alder. At its most basic, it is a 4+2 cycloaddition. We call it a 4+2 because we have 4 pi electrons here. Remember, this is a double bond, means it has a sigma bond and a pi bond. And each bond is a pair of electrons. That sigma bond has 2 electrons, the pi bond has 2. And since we have 2 pi bonds here, there's a total of 4 pi electrons. There's 1 pi bond here, and so we have we have 2 pi electrons, hence the name 4+2. What's going on during the reaction? 1 pi bond breaks, forms a new sigma bond to the dienophile. This one then, that pi bond breaks, forms a sigma bond to the diene, the other double bond, and that pi bond breaks, forming a new one between the two. And so the product that we get, and we're starting with our butadiene, we're forming a new bond to the alkene over here, and then that pi bond breaks, so it's now a single bond, but we formed a new one here, and we end up with our double bond there. And so I'm going to number these just so we can keep track of what's going on. If we number it 1, 2, 3, 4, 5, 6, the same numbering, 1, 2, 3, 4, 5, 6. You can see the carbons that correspond. But this is a Diels-Alder reaction in its most simple form. And it is, in fact, what you did for the lab reaction. You had a diene, you reacted that with a dienophile, and you formed a cyclohexene. In the case of the reaction that we did in lab, the diene had a lot of other detritus hanging off of it, but it is still basically a diene. So for example, we have the 2 double bonds here for our diene, we have 2 double bonds here. We have our dienophile, we have that double bond. In this case, we have a triple bond, but still we have that 1 pi bond that can react, and when that pi bond reacts, it will break. So in the initial example, since we only had 1 pi bond, we end up with 1 sigma, or a single bond at the end. In the reaction we did with the benzyne, we have 2 pi bonds in the benzyne. One of them is going away, but the other one stays, so we end up with a double bond in the end of that. So we have this cyclohexene, we have the cyclohexene here as well. This other double bond is coming from here. It is that triple bond being reduced to a double. But again, we're getting the cyclohexene from our diene and dienophile, but all of that other stuff is still hanging out on this thing. So for example, we had those 4 phenyl rings on our diene. Those 4 phenyl rings are still present. We had this carbonyl. That carbonyl is still present. And here we had that benzene ring. That benzene ring is also still present. So we simply do the diene plus dienophile, giving us the cyclohexene, but we remember that all the other stuff goes with it. And so we end up with this intermediate. Of course, under the reaction conditions we did, that intermediate is not stable, so we lost that carbonyl as carbon monoxide, and we end up with the tetraphenylnaphthalene, our final product. Of course, there is one more reaction that we need to keep in mind for the Diels-Alder. Like the Grignard reaction, we actually have two reactions that are going on. First, we made the Grignard reagent, then we did our reaction with the aldehyde. Same thing here. The first step was to make the benzyne, and we did that with the amino-benzoic acid, also called anthranilic acid, in the isoamyl nitrite. And that made the benzyne. Again, you should be familiar with the reactions. You should be able to do a Diels-Alder for a related species. If it forms an unstable intermediate, we are not going to expect you to recognize that intermediate is unstable. We would expect you to stop there. But we also expect you to understand why you did the various steps. For example, how did you remove the dimethoxyethane, the solvent for the reaction? How did you purify your tetraphenylnaphthalene? So be familiar with the techniques you employed as well. Move on to various techniques. You should recognize this apparatus, or if you're asked about a reflux, you should be able to draw it or select it if you have a choice of various setups. You should understand what a reflux is and how it works. Remember, for reflux, we are adding water always into the lower vent that fills this outer jacket with water, and that provides cooling for that inner column. And of course, water comes out of that upper vent up there. We use reflux to heat, so we would have a solution down below that we are heating. As the sample gets hot, it starts to vaporize. We get vapor formation, and the vapors will rise up into the column. But once those vapors, those hot vapors, come in contact with that glass, because it's being cooled by that water jacket, those vapors will condense and they will drip back down into the round bottom flask. That's what the reflux means. It means that it is going up and then coming back down, continuing to recycle. The reason that we do reflux is to primarily, we are using it as a means for controlling a heated reaction, but we do it specifically to accelerate the reaction rate. A general rule of thumb that you learned in general chemistry is that for every 10-degree rise in temperature, you double your rate. The rate is increased twofold. So we could take a reaction that occurs in maybe, say, 8 hours at room temperature. If we do that reaction in, say, refluxing methanol, we're raising the temperature 40 degrees, so we get 4 doublings, and so the reaction will occur in just a half hour. So that's the primary reason we heat the reactions and reason we're refluxing. There is a secondary reason for reflux. We could heat a solution in, say, just a beaker or in the round bottom flask without the condenser, but if we did that, the solvent would be constantly boiling away, so we use reflux specifically to conserve the solvent. This also allows us to do a reflux for a long period of time. So for example, you could start a reaction and let it run overnight. With the reflux condenser, you never boil your solvent dry. Whereas if you tried to do that in just a beaker, you would quickly boil all your solvent away. This technique is addition under reflux. The main purpose, of course, is for the reflux is to heat so that you can accelerate your reaction. But we use this technique so that we can also add a second reagent or a third reagent, whatever. We can put something in that addition funnel and we can add that to the reaction mixture while it is under reflux. This is a technique that you employed in the Grignard reaction. So while the Grignard reagent was at reflux, you could slowly add the aldehyde. Also in the Diels-Alder, you could put a slow addition of the isopenyl nitrite to the anthranilic acid so that you could form the benzyne but do it slowly to keep the concentration low. This is a separatory funnel. The technique is either called extraction or washing. From a practical standpoint, it's the same thing. You combine your two liquids, you swirl, you vent, you invert back, and then drain out one of the layers. So from a practical standpoint, you're doing the same thing. We call them extraction or washing depending on what's going on inside the separatory funnel. In an extraction, the desired product, the stuff you want, is extracted from one solvent to another. Whereas when we are washing, the material you want stays where it is, but we are removing instead impurities. So for example, with the dehydration experiment, you had your alkenes, and we say that you washed it with a sodium bicarbonate solution. The alkenes did not go into the aqueous layer. They stayed where they were. They were part of, in fact, they made up the organic layer. But instead, when you were doing the wash, you were removing residual acid. Hence the term washing, because we are cleaning the material up. The impurity was washed out of the solution. For the Wittig reaction, you were doing an extraction. You'll recall that you had your reaction was done in ethanol. You added water to that to make a 50-50 mixture. And then you extracted with hexane. We called it an extraction because the stuff you wanted, the alkenes, moved from that aqueous methanol or ethanol layer into the hexane. So the product was removed, and the stuff we did not want remained behind in the aqueous layer. A few points about extractions or washing. It does require two immiscible solvents. So you cannot extract from an aqueous solution, for example, you cannot extract with ethanol. As you all know, ethanol and water mix. If you buy a beer or some other drink, you do not have water layer and an alcohol layer. They are combined. They mix. So you cannot do an extraction with those. The two liquids cannot dissolve in each other. They are immiscible. The more dense layer will be on the bottom. Usually, the organic layer will be on top, because most organic solvents are less dense than water, but there are exceptions. In particular, halogenated ones, but there are other exceptions, so you do need to know the densities of the organic layers. And typically water we can assume is going to be around 1 unless it is a fairly concentrated solution, in which case it could be greater. Neutral organics tend to dissolve in the organic solvent, and inorganics and organic salts dissolve in the aqueous layer. For example, in the ester hydrolysis reaction, after the addition of the base and you refluxed, the initial product was the sodium carboxylate salt. This is an organic compound, but it is also a salt, and so it was in the aqueous layer, and we washed it with ether. And the reason you washed with ether was to remove things like the alcohol, the other product for the reaction, but also any unreacted ester that you had. Both of those, the alcohol and the ester, are neutral. They're not salts. They're organic, and so they would have gone in the ether, the organic layer. And the salt remained in the aqueous layer until you acidified it. As you will recall from that, you added some hydrochloric acid. When you acidified it, you converted it from the sodium carboxylate salt into the carboxylic acid. And so now it is not an ion, it is a neutral compound, neutral with respect to ionization. And so it is organic, it is no longer water soluble, but in this case we did not extract it, simply precipitated out of solution. The technique you employed was drying a liquid. Obviously, the liquid in question would not be water, since you cannot dry water, but the drying refers specifically to the removal of water, and for that we use anhydrous salts. Something like sodium sulfate will combine with water to form a hydrate, and specifically with sodium sulfate you can form up to a decahydrate. If you did general chemistry here, you would have done the reverse reaction where you took the hydrated salt, heated it, and made an anhydrous salt, and then you determined the waters of hydration. This is the reverse. From a practical standpoint, you simply add some of the drying agent to your liquid, you swirl it around, give it time for the salt to absorb the water. If the salt is all clumped together, it's not dry. If some of the salt remains free-flowing, then it is dry and you've added sufficient salt. A second method that can be used is to wash with a saturated salt solution. This is a technique that you employed, for example, in the Grignard reaction. You washed with a saturated sodium chloride solution. Of course, it was dissolved in water, so it was aqueous. We used this to remove water from specifically ether. A number of ethers, diethyl ether was the one you were using, will absorb a significant amount of water. They doesn't mix completely, so it's not miscible, but you can absorb a fair amount of water, and so we do an initial wash with saturated sodium chloride, and that removes most of the water. Of course, to get the last traces of water, we then added an anhydrous salt to the ether to remove the last traces. But to get the bulk of the water out first, we washed with a saturated salt solution. Then, of course, another technique is melting point. We obtain melting points for characterization. The technique is fairly simple. You obtain a small amount of your material, you heat it, and you watch for it melting. The apparatus we use, the Meltemps, you put a small amount in a melting point capillary and start heating the sample, and you watch the temperature as it starts melting. And of course, the thing you're looking for is that you have a sharp melting point that tends to indicate that it is pure. A broad melting point means that it is likely impure, and then also the measured melting point should be in the same range as the reported or literature melting point. If the melting point is low, that also indicates impurity. The more impurities you have, the greater that melting point is going to be depressed. And so low melting points and broad melting points indicate you have an impure sample. Another technique is rotary evaporation. This is a technique that's used to remove solvents from non-volatile substances. Obviously, if you try to do this with a volatile substance, it will probably come off. It will evaporate along with the solvent. We use this specifically because we can remove the solvent at low temperature, typically room temperature, which means we don't run the risk of decomposing it. You could also remove solvent by doing a simple distillation. The problem is you are heating that round bottom flask, and you run the risk that the residue that's left behind, which is the stuff you want, you're not after the solvent, you are after the residue that's left behind, you run the risk of decomposing that if you're heating too strongly. And hence we use rotary evaporation. This is essentially a vacuum distillation. As you know, lower pressure means a lower boiling point. This is the reason that we correct boiling points here in Boone. We're at higher elevation, so the atmospheric pressure is a little bit lower, and so we have to correct our boiling point for that. In a rotary evaporator, we are lowering the pressure to a much greater extent. We're putting it under vacuum, and this allows us to lower the boiling point to room temperature or even lower. And so we can boil that solvent at room temperature. Another technique you've used is trituration. This is also a technique used for purifying solids. Basically, it means to grind a solid under solvent. So you would place your solid in a flask, add some solvent, and simply start grinding it up. You want to break it to a fine powder, and this allows one substance to dissolve while another remains behind. So you do want to pick a solvent that will dissolve either your product and not the impurities, or the impurities and not your product. Specifically, we use this for the Diels-Alder reaction, and you used it to purify the tetraphenyl naphthalene. In this case, we used methanol, and the tetraphenyl naphthalene was insoluble. So you filtered it, and you isolated then the TPN, and the impurities which dissolved went out into the filtrate. You could use this technique for the opposite as well. If your product is soluble, it will dissolve in the methanol or whatever solvent you're using. The impurities would be insoluble, so when you filter, the impurities are on the filter paper, which you would then discard, and your product is in the filtrate. So obviously you'd want to use a clean filter flask when you do this. So in this way you're purifying the solid, although it is still dissolved in the solvent. So that raises the question then, how do you isolate your product from the solvent? And I will leave you to figure that out. If you're having trouble, you might want to go back a few slides to find a technique that is used to remove solvent from a substance. So we'll move on then to calculations. One of the calculations that you've done in lab and you will undoubtedly need to do on the final exam is calculate limiting reactant. The best way to approach that is to calculate the theoretical yield for each reactant. If you have 3 reactants, you'll do 3 theoretical yield calculations. If there are 2 reactants, you'll do 2 theoretical yield calculations. For theoretical yield, you simply take the amount of substance that you measured, whether you weighed it, if it was a solid, or volume for a liquid. You would calculate the number of moles, look at your mole ratio between reactant and product, and then calculate the mass of the product that you would get. And you would do that for each reactant, and whichever one gave the least amount, that is your theoretical yield, and also that identifies the limiting reactant. Something to keep in mind here is that if you are dealing with solutions, you need to remember the equation MV equals moles. The molarity times the volume tells you how many moles of that particular reagent you have. If you're dealing with a pure liquid, you would use density to convert volume to mass, and then you would use molecular weight to go from mass to moles. But for a solution, you must use the molarity and the volume to calculate moles. And then percent yield is the actual yield divided by the theoretical yield. Again, this would be for the limiting reactant. We'll add times 100% because you do need to make this a percentage, but it is actual over theoretical. Density is mass over volume. So you would simply take the mass divided by the volume, although typically for chemistry we express the mass in grams and the volume in milliliters. So you should convert to grams and milliliters if you have other units. As I've mentioned already, you have to correct for boiling point. If you are in Boone, the boiling point will be about 3% low. This is because we are at a higher elevation and therefore have lower atmospheric pressure. And as pressure goes down, boiling point goes down. So for corrected boiling point, we would take the measured boiling point and multiply by 1.03. So we are increasing by 3%. Another technique or calculation that you did was coupling constant, JHAB. This is the coupling constant between hydrogen A and hydrogen B. So these would be two hydrogens on adjacent carbons, and we are measuring the coupling constant between those two hydrogens. And that's what the J stands for. To do that, we measure the difference between two peaks in the same multiplet. Notice that I have both of these labeled as HA. HA. So we're looking at one peak and a second peak for that multiplet for HA. So they must be adjacent peaks in either a doublet or a triplet or a quartet, whatever. And we multiply that by the field strength of the magnet. And the field strength would be expressed in terms of the frequency in megahertz, or excuse me, hertz per ppm. So for example, we have a spectrum here. If we are trying to measure the coupling constant for that doublet, and this would be, say, HA, and this one here would be HB. We do not take the difference between those two doublets. Rather, we take the difference in chemical shift between two peaks within the doublet. So for this, we would have the 7.1394 minus 7.0995. So we're taking the difference between those two adjacent peaks. When we do that, we get 0.0399, and we would multiply that by our B0. For our instrument on which this spectrum was recorded, the frequency or the field strength for the magnet is 400. That would be 400 megahertz or 400 hertz per ppm. So this is converting ppm to hertz, and we would get for this 15.96 hertz. So that would be our coupling constant. And so the equation is shown there. But again, remember, this is two adjacent peaks of the same multiplet. So if you had a quartet, you would measure difference between these two peaks, or these two, or these two, but they have to be adjacent peaks within that one multiplet. One other calculation, and this is also with alkenes. Specifically you did this for the Wittig experiment. This is the estimated chemical shift for a vanillic hydrogen. And so we start with the base, the 5.25, and we add the effects of the geminal, cis, and trans substituents. I go into some detail on this in another video. I'll have a link below in the description to that. But just quickly here, if we're looking at an example, we have this compound here. This is called cinnamaldehyde, but we have the HA and HB. And so we would start with the base, the 5.25, add the impact that the geminal group has. And so geminal is the one that's on the same carbon. So if we're looking at HA, this is the geminal group. It is a substituent on the same carbon. We would add to that the effect of the substituent that is cis, and so cis is on the opposite carbon, but the same side as HA. So this is cis to HA. And then we would add the effect of the substituent that is trans, and the trans group is HB. This is the one that is trans to HA. And of course, since the base compound is one that had hydrogens in all positions, the effect of another hydrogen is 0. And so we would simply go to the table. 5.25 for HA, we're looking at a geminal aromatic. So we would come to the table, we would go to aromatic, and specifically we would go to the geminal, so we would add 1.35. Then we would add the effect of the cis. So the cis, up here we have a ketone, so we would come to this group here, and for the cis we have 1.13. One thing to note here is that we do have 3 different carbonyl containing compounds in this table. We have a carboxylic acid, we have an ester, and we have a simple carbonyl, which would apply to ketones and aldehydes. It is important to use the correct one. You'll notice, for example, the geminal, we have a substantial difference between the ketone and the ester. 1.1 versus 0.8, so it's almost a quarter of a ppm. Same thing with the trans, we have about a quarter of a ppm difference between those two values. So they can be significant, which is why they're listed separately. You do need to pay attention to what the group is when you are doing these calculations. You may be expected to know the equation. It is fairly trivial, but if you are asked to do these calculations, you will be given the table. We don't expect you to memorize the table for the substituent effects. Now we will move on to chromatography and spectroscopy, IR or infrared spectroscopy. The peaks in infrared spectroscopy give us information about the types of bonds. So peaks specifically correlate to specific bond types. For example, if we have a strong absorption between, say, about 33 to 3600 inverse centimeters, we also refer to those units, the inverse centimeters or 1/centimeter, as a wave number. A peak around 33 to 3600, a strong absorption in that range, correlates with an OH bond for an alcohol. So this is specifically a stretching vibration, but it tells us that we likely have an OH. The strength of the absorptions are important. For example, polar bonds, OH and carbonyl in particular, tend to be strong absorptions. Non-polar bonds tend to be weaker ones, although for things like CH, you may have many carbon-hydrogen bonds and therefore many carbon-hydrogen stretching frequencies all in the same range. They pile up, and so you can have a strong absorption simply because there are many weak to medium absorptions. But you do need to memorize that table that's given in the pre-lab about spectral interpretation, and I will include a link in the description below this video to a video in which I discuss the interpretation of an infrared spectrum, and you should memorize those major frequencies that correlate. The ones above about 1600. Things below 1600 are fingerprint, and we often have different bond types that vibrate or absorb in the same region, and therefore because of that overlap, it's difficult to say without knowing what the compound already is what type of bond that is. And so we usually ignore the region below 1600. But you are not likely to have that table on the final exam, so you should memorize that. We'll look at one quick example. So this is an infrared spectrum. Again, peaks come down. We do have particular regions that we tend to look at. So I mentioned the 33 to 3600 region. With infrared spectroscopy, since we do not have anything in this area, no strong absorptions, this tells us that we have no OH. The compound is not an alcohol. And so for infrared spectroscopy, the peaks that you do have are important, but also the peaks that are absent can tell you something about at least what isn't present in your compound and give some clue as to what you do have. In the about 2700 to 3100 region, we find CH, but we have a particular demarcation line at 3000. So peaks that are between about 3000 to 3100 are CH, but specifically it is sp2 hybridized CH bonds. So this would be carbon-hydrogen bonds on an aromatic ring or that are part of a carbon-carbon double bond. And so this suggests we have an alkene. Likewise, these peaks also in this region are CH, but because they are below that 3000, these are sp3 CH. And then we also have this peak here at about 1642, but this is the range, about 1600 to about 1670 or so is where we find carbon-carbon double bonds. So this suggests we have an alkene. Out in the range of about 17 to 1800 or 1850, out in this region, we would typically see strong absorptions if we have carbonyl. The absence of that tells us we do not have an ester or an aldehyde or a ketone or carboxylic acid or other groups that contain that carbonyl. So this is how we interpret infrared spectra. And as I mentioned, I will put a link to the video if you want to see a bit more about that. So from here we will move on to nuclear magnetic resonance spectroscopy. Specifically, we're going to talk about proton or hydrogen NMR to start. There are other nuclei besides hydrogen that are NMR active. But again, as with IR, you should learn the various regions that are involved. So again, look at the correlation table and learn the ones that are relevant to the various compounds that you have made or used during the semester. And again, I will provide a link to my discussions on NMR spectroscopy. They are part of videos that deal with other experiments. You can just jump to the NMR discussion and ignore the rest of the video if you need to have a refresher on that. But you should be able to interpret a spectrum. So if you're given a spectrum, you should be able to look at it and determine which compound that represents from the spectrum or even from the spectrum alone. For infrared spectroscopy, of course, you don't get particular compounds, but you get functional groups. So for IR, you would probably should be able to at least determine what functional groups are present, and if you had a list of compounds, match a particular spectrum to a particular compound based on the peaks that are in the spectrum and the bond types that are present in the structure. But for NMR, you should be able to get individual structures from the spectrum alone without having any idea really what it is or what you think it might be. My recommended procedure is to start with integration. Integration will tell you whether you have a CH or a CH2 or a CH3, or if you have something like an integration of 6 hydrogens, that you probably have 2 methyl groups. But the integration then gives you that type of information. My recommendation is the next step is to look at the chemical shift to determine the type of hydrogen. For example, is it an alkoxy? Is it OCH? Is it in the alkyl region, just an ordinary CH, aromatic region? So you want to look at the shift to determine the type. And then the final step is to put the pieces together. And for that, you will use the splitting. The splitting tells you how the various pieces you've identified go together. For example, you might have a peak at 3.8 ppm. This is in the alkoxy region. So the chemical shift tells you you have a OCH. The integration tells you it is 2 hydrogens, so you know you have an OCH2. If the splitting for this is a triplet, then that would tell you it is bonded to a CH2, so you know then that it is bonded to a CH2. And you can look at the other peaks, find out which ones have an integration of 2, and then determine which one that's bonded to. And again, you would look at splitting. For example, if the splitting for this one is a pentet, that would tell you that it has 5 neighbors. Because of the bonding that we already have, we have 2 neighbors here. So we have 2 of the 5, which means it has to be bonded to 3 more. So on the other side, we have to have a CH3. And of course, we would want to confirm that. We would look at the splitting here. And since it has 2 neighbors, this should be a triplet. If it isn't a triplet, there's a problem, and of course you'd need to resolve that. But all the splitting should make sense for putting these pieces together. And again, I'll have a link to a more in-depth analysis where I actually look at a couple of examples so you can see how that is done. Now we've used the proton NMR for further analysis for alkenes in particular. So you should be able to use the NMR spectrum to identify the geometry of an alkene. Specifically, is it E or Z? Or if you prefer, trans or cis. There were 2 methods that we used to make that determination. One, we used our coupling constant, which I've already mentioned in the discussion of calculations where we talked about that. For trans alkenes, the coupling constant is typically going to be in the 14 to 18 Hertz range. So if you see a coupling of that magnitude, this is probably a trans alkene. For cis alkenes, typically the range is going to be about 10 to 13 Hertz. And so you can make that distinction between cis and trans by which range it falls in. And they are fairly well separated. This is fairly reliable. Of course, it's nice to have another confirmation. We did have a second method that we used to make that determination. Before I get to that, though, we're going to look at an example. So for coupling constant, this is the example we looked at before. We took the difference between those 2 chemical shifts, multiplied by 400, and we found that we had a coupling constant of 15.96 Hertz. So this is in that 14 to 18 range. So this is a trans coupling, suggesting this is a trans compound. And we could do the same thing, take the difference here, and again multiply by 400, and we again get a coupling constant of 15.96 Hertz. Of course, we should get the same value. There may be some error in that last place, typically rounding error, so they may not be exactly the same, but they should be very close. But again, this indicates that we have a trans isomer. All right, so the coupling constant is one way to determine cis and trans. There is a second method, and often we will use these in concert. Hopefully they both give us the same answer. If not, we might be a little concerned about our assignment of stereochemistry. But if they both tell us the same thing, then we can be fairly confident about that. And the second method is to use a calculated chemical shift. The delta, of course, means shift. And so we would want to use that formula that I again mentioned in the calculation discussion and do that for both the cis and the trans isomers and then compare that. So this is the example I gave before, and we have the chemical shifts for the trans isomer, the calculated shifts. We could do the same thing for the cis isomer, and so we now have those chemical shifts for that. At this point, we would go to the spectrum and compare these numbers with the actual frequencies or actual peaks in the spectrum. So again, we have these calculations that told us they were trans, but now we would look at the chemical shifts that we calculated. So for the trans isomer, the values that we calculated were 7.73, which would be right about here. So this is the first trans peak. The second one was at 6.72, and we would compare the fit of the actual peaks we see with the calculated shifts to that for the cis. The cis peaks were at 7.41 and 6.25. And we see in this instance that those two doublets are a much better fit to the trans calculations. One is the one that's at 7.1 ppm is not a good fit to the 6.72, but it is closer than the 6.25. Whereas the peak at about 7.77 is a very good fit for the 7.73. Certainly better than the 7.41. The calculated shifts for the trans peak fit the actual peaks we see much better than the calculated shifts for the cis, and so we can be fairly confident that this is in fact then the trans isomer of the cinnamaldehyde. But this is how we use those calculations to determine whether or not our product, or whether our product is cis or trans. If it was a mixture of both, we should see peaks that correspond with the cis as well. And we would have the coupling constants for those, as you did with the Wittig reaction. You had peaks that fit the calculated shift for trans, as well as a pair of peaks that fit the cis fairly well. But we also had coupling constants for both that fit both the cis and the trans. And so in the example that we just looked at, the calculated shifts matched trans isomer, and the calculated coupling constant also matched for the trans, and so we could identify our compound as being a trans isomer. So from here we will move on to carbon-13 NMR. Again, you should know the general areas that peaks absorb in. The compounds you'll be looking at will be similar to the ones that you analyzed in lab, so you won't be seeing something totally unique. So basically, carbonyl and aromatic regions, alkene region, which overlaps aromatic, but you should know those regions. The type of analysis, again, will be very similar. So with the tetraphenyl cyclopentadienone and the tetraphenyl naphthalene, you could not make individual assignments. Again, I will refer you back to the video that I did for that, and I will have a link again below for that. But again, what you could do is look at the peaks and make some general assignments. Certainly the carbonyl is very distinct, and you could distinguish that. The aromatics were all overlapping, but you could make a few distinctions based on basically the peak height. There are two factors that control peak height. One was the nuclear Overhauser effect, or NOE. Basically, carbons that have hydrogens tend to be taller. Carbons that don't tend to be very short. And so using NOE, we could identify the very short peaks as carbon without hydrogen. So carbons that have no hydrogens were the very short peaks. The other factor that affects peak height is the same thing that affects peak height in proton NMR, which is the number of equivalent carbons. So the taller peaks were all peaks that have carbons that have hydrogens. And so where we saw a difference in peak height, that difference in peak height was due simply to the number of equivalent carbons. So for example, if we had a carbon spectrum, we have a very short peak, and then we have a couple of taller peaks where one peak is roughly twice the size of the other. This would mean that this is a carbon with hydrogen, but there are 2 times as many as for this one. So we have this ratio. And the very short peak would be carbon without hydrogen. And so that is the kind of distinction that you needed to do for your report, and it is the kind of thing that we expect you to be able to do for the final exam. And so you would make the same type of analysis. Well, this one is ipso, this is para, this is ortho or meta, that type of analysis. All right, and we will finish then with UV and Gaussian. Again, what you can expect on the final exam will be similar to what you did for your report. So for the analysis for the report, for the ultraviolet and visible spectrum, the thing that we were looking for was primarily relative levels of conjugation. And of course, there should also be something with respect to color. Very simply, if a spectrum has peaks greater than 400 nanometers, it is colored. The compound is colored. So if a spectrum has peaks greater than 400 nanometers, or wavelengths longer than 400 nanometers, the compound's going to be colored. If all of the peaks are less than 400 nanometers, then the compound is not going to have any color. It is colorless, or often we'll say it's white. Of course, if you pick up a single salt crystal or a single sugar crystal and look at it, you'll find it is colorless. But of course, when you have a whole bunch of them together, because of diffraction, it looks like it's white. But basically, colored compounds absorb at wavelengths greater than 400 nanometers. For relative conjugation, what we are looking for is the longest wavelength peak that we see in the spectrum. The spectrum may have multiple peaks, but we don't care about the shorter ones. What we want to look at is the longest peak. The longer the wavelength, the more conjugated the compound is. And so if we are comparing two spectra, if one has, say, a peak at 350 nanometers and the other has a peak at 425 nanometers, the spectrum with the peak at 425 is going to have a more conjugated product. And so that's all we looked for with the UV visible spectrum with respect to lab. We didn't try to look at chromophores and determine, well, we have a peak at, say, 250, which is a chromophore for a particular absorption for aromatic compounds. We're not interested in that. Simply which one is more conjugated. And that is pretty much what we did with the Gaussian as well. For the Gaussian images, we were looking at the highest occupied molecular orbital, which we abbreviate as the HOMO. And basically, the more carbons that were involved that had lobes in the HOMO, that represented more conjugation. So more carbons with lobes in the HOMO is greater conjugation. And that's what you were looking at when you compared the tetraphenyl naphthalene to the tetraphenyl cyclopentadienone. And we were using the UV in concert with the Gaussian as a means of not so much confirmation, but possibly exclusion. When you make a comparison, is this one more conjugated than that? There are a lot of compounds that might fit that. So using this as a confirmatory test isn't very good, but we can use it as an exclusionary one. For example, let's say the UV visible spectrum said that the tetraphenyl cyclopentadienone had more conjugation or greater conjugation than the product. Remember, we made a product that we believed was TPN, but we want to confirm that. We don't know that it's tetraphenyl naphthalene, but we assume that it may be. We want it to be. So we have UV visible spectra of both the TPC, the starting material, and the tetraphenyl naphthalene, and we compare those. And the UV says that the TPC is more conjugated than the product. And then we compare that to the Gaussian. And the Gaussian says TPC is more conjugated than TPN. Well, under this scenario, our product may be TPN. This is not a guarantee it is, but it suggests it may be. On the other hand, if our ultraviolet spectrum said that TPC was more conjugated than our product, but the Gaussian said the opposite, TPC was less conjugated than TPN, this would definitely exclude the TPN as the product. This would tell us that our product is not TPN. So we have excluded that. So this is more of an exclusionary method, but you compare them. If they tell us the same thing, then they may be the same. If they tell us the opposite, then we can be sure our product is not that particular compound. Okay. And so you should be able to do this sort of analysis as well on the final exam. Given two UV visible spectra and two Gaussian images for the HOMO, you should be able to determine, is this likely to be the same compound or is it not the same compound? What we're looking at here is a mass spectrum. You should recognize, for example, the peak at highest mass. This is going to be our parent ion. This tells us the mass of our product, which is 216. In this case, we have our M+, but we also have an M plus 2 peak that is 1/3 the size of our M. This is an indication that this material, whatever it is, has chlorine. So the larger peak is the fragment that has a chlorine 35 on it. The larger peak is 2 mass units higher because it has chlorine 37. And since the mass spectrum, we're looking at individual molecules or fragments as they come through, individual ions, they will have specific masses to that particular isotope. But we can then look at other peaks as well. This one, we have our M, but there is no M plus 2. So this one does not have chlorine. Whatever this fragment is, there is no chlorine on it. This one we have an M plus, and we have an M plus 2 that is 1/3 the size. So whatever this fragment is, it has chlorine. Likewise, the 111, we've got the peak. This one has chlorine. This one, there is no M plus 2 that's 1/3 the size of the M. So this one does not have chlorine. So we can make identifications about various fragments and whether or not it has chlorine in it by looking at these isotope peaks. Of course, you can also get some information about the fragments by looking at, for example, here the difference between the masses. We have 216, 181. When we take that difference, we get 35. This matches the mass of chlorine, so in fact, the peak at 181 is the parent ion after it has lost chlorine. All right, this mass spectrum should look familiar to you. This is the product you made, and again we see this M and M plus 2 indicating that whatever this is, it has chlorine. And again we see the M and M plus 2 here. But you should also be able to look at the difference between the masses of these two peaks, for example 210 and 182, and recognize this as a loss of 28. And you should recognize certain items like this, the 28, being equivalent to loss of an ethylene, and that something like this is an indication of the McLafferty rearrangement. And recognize what that means. For a McLafferty, you have to have a structure such as this. And you're getting a rearrangement, in which case you are losing this as a CH2. One of these hydrogens ends up over here on this oxygen. An X can be a carbon, can be an oxygen, could be a nitrogen. So you have different options, but this is common with ethyl esters. And in fact, you could continue the same thing going from our 210 out to 165. And when we take our difference here, we have a mass of 45 that is lost. And you can recognize that a mass of 45 is an ethoxy. And you can add that up individually if you need to. Oxygen 16, each carbon is 12, so for 24. Hydrogens, we have 5 of them. And if we add this together, we then have our 45 for a mass. But this indicates that whatever we had, we knew we had this propyl chain here for the McLafferty. Given that we are here losing an ethoxide, tells us the X is O. But you should be able to look at this, recognize the loss of fragments, and determine what those fragments are, what is lost, but more importantly, what this is that's left behind. So you should be able to interpret mass spectra for your final exam. In addition, you should be able to use a gas chromatograph or mass chromatogram to identify various peaks that you may have and use that for some of the calculations. So here we have area percent. So if we identify, say, this peak as our product, you should be able to take the retention time, match that to a retention time down here. We have an area percent then of 66.5%, meaning that whatever was injected, 66.5% of it was our product. So another calculation that you should be able to do for your exam would be to calculate then a crude yield and a crude percent yield. So let's say, for example, you weigh out a final product mass of 9.36 grams. In the example that we just looked at, only 66% of that is your actual product, so you would multiply this by 0.665, which of course is the decimal value of the percentage, and you would get a final mass of your product, which is 0.622 grams, meaning that of the crude mixture, so this is product plus other stuff, only 0.622 was crude product. And we use that term crude to indicate that it is part of a mixture and not purified. If you say that you have 0.622 grams of product, you're implying it's purified, so we use that term crude. And likewise, you would need to be able to do a crude percent yield, but again, you simply take this value, which is the actual yield of product, and you would divide that by theoretical. You did this for the optimization experiment, and you should be able to do these kinds of calculations for the for the final exam as well. So let's look at NMR spectroscopy. This is a proton NMR. You should recognize the various regions in the spectrum. For example, between about 3 to 4.5, this is the alkoxy region, meaning that this is an OCH of some sort. Typically between 2.7, this is the region where we find benzylic and allylic. So this would be a CH that's next to a double bond of some sort. Given that we have peaks down in this region, this is typically going to be in the vinylic region. It's a little low to be aromatic, although the vinylic region does extend really from about 5 at the low end, could be up as high as 8, very broad region. It's a little low for aromatic, although there's a lot of overlap. The aromatic tends to be in this region here. So these other 3 peaks here could be aromatic and or vinylic as well. Of course, one way to determine that, if you have a vinylic compound, is to do those calculations that we talked about above, the 5.25 plus Z-gem plus Z-cis plus Z-trans, and that will give you an approximate chemical shift, and you can use that then to determine what your peaks are. Of course, you should be able to look at splitting and recognize what kind of neighboring environment the peaks are in. So we have a doublet here, tells us there is one neighbor, and so it is next to a CH. Likewise, this one doublet next to a CH. You should be able to look at integrations. Typically, when you were processing these yourself, you were able to look at integrations and set them using the computer, but you may not have, well, you won't have that option on the exam, and they may not be given as whole number integrations, in which case you should be able to calculate ratios. For example, we have a ratio of this one 1.59 to this 1.62. You could divide both of these by 1.59, and if we do, this is 1, divide by 1.59, and this is essentially 1, so it's a 1-to-2 ratio. We could also do the same here, 4.85, divide by 1.59, and it is essentially 3. The actual value is 3.05, but of course we would round that to 3, to the nearest whole number. But that also tells us that we are dealing here with an OCH3. Likewise, 4.97 is also equal to 3. Again, it's not far enough away that we would round otherwise, so we get this 3, and this is also then a CH3, again, probably bound to an aromatic ring, since we do have these that doublet out there around 7.2 and 7.4. And those integrations give us 2 hydrogens. And so this is likely, given the chemical shift, one that's bonded to the benzene ring. So it's likely a benzylic methyl. You should be able to do this kind of analysis. Of course, given the calculated chemical shift, you would be able to tell that this is one of the vinylic hydrogens and this is the other. In fact, if your structure is one of a double bond where each carbon of the double bond has a single hydrogen, given that these integrations are each one hydrogen, you should be able to recognize then that these are the vinylic ones. But you should also be able to calculate J. Mentioned this when we were talking about calculations. J is equal to the difference in the shifts of the two peaks within the multiplet. So if this is HA and this HB, we are not subtracting 7.7 from 6.4. We are subtracting the value of the two peaks of that multiplet. So we are taking these 6.4423 minus 6.4023, and this is what we are multiplying by our spectrometer frequency, in this case 400, and it may be something else. If so, you will be told what it is. And the difference here is 0.0400 times 400, so this is math we can actually do in our head. It's 16.0. The value here is hertz. And you should recognize that this is a trans coupling. Remember, trans coupling constants are in the range of roughly 14 to 18 hertz, and that is solidly in the middle. And of course, cis couplings are typically about 8 to 13 hertz. And so you should be able to calculate a coupling constant and use that to determine whether you're looking at a cis vinylic hydrogen or a trans geometry. And you should be able to get the same identification of cis-trans if you look at calculated values for the cis versus the trans and see which ones best match the peaks you're looking at. Here we have another NMR spectrum. This one a little more complex. Here we do have essentially whole number integrations. These two, for example, are definitely whole numbers. This is close enough that you can round. But again, recognize that this is in the region of OCH. Given the integration, it is 3. This peak, likewise, at 4.1 is also in the alkoxy region, so this is again an OC. Integration of 1, so it's an OCH1. So you should be able to recognize that aromatics, CH2 doublet, meaning that we almost certainly have, since we have 2 doublets, this is going to be a para-substituted compound. If it was something other than that, we would not have 2 doublets. So we've got other things attached to the other sides of that aromatic ring. But you should be able to recognize this doublet indicating this is next to CH has one neighbor, meaning it's bonded to a CH. This peak, if we blew that up, you could see that it has, this one actually has 8 peaks, so this is an octet, meaning it has 7 neighbors, meaning, well, there's several options. You could have the likely one, 2 CH3s and 1 CH would give you 7 neighbors. So you have something like this, and this is the peak here, and it's bonded to 2 CH3s and a CH, and that would give it the 7 neighbors. In fact, if you go back to the other peaks that we were looking at, we said this is bonded to a CH, it has 1 neighbor. This is a doublet, so 1 neighbor, it's bonded to a CH. And this one also, a doublet bonded to a CH, so these are probably those 2 CH3s in the CH. There are, of course, other ways you could get 7 neighbors. You could have a CH3 and 2 CH2s, but again, we don't have peaks that integrate to 2 hydrogens, so having a CH2 is not an option for this particular molecule. But again, you should be able to make these types of analyses in a proton NMR spectrum. So know your splitting, know integrations. In particular, you should be able to take values that are not whole numbers and get the whole numbers, and the simplest way to do that is to divide all of the values by the lowest, and that should give you something approximating whole numbers. And you should know your regions. Know, for example, that this is alkoxy, this is benzylic, allylic, and be able to do an analysis in that way. This will actually be useful if you have a reaction and you're not certain what the product is. If you look at the spectrum and you can interpret it, you can work backwards and get that structure. For example, with this one, again, we have this pair of doublets integrating to 2 each in the aromatic region. That pair of doublets, as I've mentioned, if you're an aromatic, indicates that you have a para-disubstituted compound. We have this benzylic peak out here. It was a methyl group, so we have this. We also have an OCH3, and we have this pair of peaks here, the ones I've labeled HA and HB. They're each next to a CH, they're vinylic, so it's almost certainly this. And we know it is trans by the coupling constant. One likely source is that this way, meaning that these are possibly bonded to each other, although in this particular case, you'd need to have a carbon or some other information to determine this. But this does have a carbonyl, and this is the actual structure of that molecule. For carbon NMR, of course, we've talked about this before, but with the carbon, of course, know your regions. This is carbonyl region. The rest of these are in the aromatic alkene region. Similar to the proton NMR, they do overlap. And so when we are looking at our analysis of these peaks, so to distinguish these, we look at essentially the height of the peaks. The shortest peaks are ones that have no hydrogens on them. So we have peaks here that all are very short, meaning these are C with 0 hydrogens, or if you prefer, no hydrogens on them. So you can do some analysis in that way. The taller peaks then, all the rest of these are carbons that have a hydrogen, and the difference in height then is going to be due to the number of carbons that are present. So we have 2 short ones here, this one and this one, that are roughly half the size of these other 4, meaning that the taller peaks represent 2 times as many carbons as these shorter ones. And these shorter ones then would be 1 carbon, and the taller ones would be 2 carbon, or some multiple thereof, 2 carbons and 4, 3 and 6, whatever. But you'll need to be able to do the same analysis. You did this for the Aldol and again for the Diels-Alder, but this is how you do that analysis. The shortest peaks don't have are carbons with no hydrogens. The taller peaks are protonated carbons, and the number of carbons is directly proportional to the number of, or the size of the peaks. So peaks that are twice the size are going to have twice as many carbons. And you should be able to do that level of analysis in the carbon NMR, same as you did in your reports for Aldol and Diels-Alder. And then finally for UV visible spectrum, again, all we're looking at is the wavelength. We're looking at relative conjugation. Here our longest wavelength appears to be around 290 nanometers. We do have other peaks, but of course we're not interested in those. We're interested only in the longest one. And note this is product. We're not identifying it as tetraphenylnaphthalene because we don't know what our product is. That's the whole reason we do spectroscopy or other characterization methods, is to confirm what we hope or determine what it is, and hopefully determine that it is our intended product. In this case, we have a peak right out here at about 502. It's at longer wavelength, and so this one we knew was our starting material, so we knew what it was. It's at longer wavelength, which tells us that it is more conjugated. The question then is this TPN? And so we need to look at the conjugation of TPN and determine if TPN is more conjugate, or excuse me, if TPN is less conjugated than TPC. If it is, then this could be our product. If it isn't, it is not our product. And to do that, we look at Gaussian structures. So when we're talking about the Gaussian, what we're looking at are orbitals. We remember for a carbon atom, we're looking at, for a p orbital, you've got two lobes, sort of like this. And these represent the two lobes of the p orbital, and that's pretty much what you're looking at in these structures. So we can move that over, and you can see there we've got our carbon is overlapping the red and the green. So those are p orbitals. So what we're looking at then in these structures, all of these clouds or blobs, whatever you want to call them, are extending over the molecule. So here we have coverage over that we have coverage over the central cyclopentadiene and the two phenyl rings, whereas in our tetraphenyl naphthalene, the coverage is only over the two rings of the naphthalene. And so we have less conjugation in the TPN than we do in the TPC. So in this case, the TPN is consistent with our product in that it shows less conjugation than the TPC. So the Gaussian shows us the conjugation of TPN versus TPC, whereas in our UV-Vis it gave the relative conjugation of product versus TPC. So TPC versus product, TPC versus TPN. And in both cases, the Gaussian is showing TPN is less conjugated, and indeed the UV visible spectrum shows it as less conjugated, and so it is possible that our product is indeed TPN. But you should be able to do this kind of analysis as well. Look at a Gaussian structure, or two of them, determine which is more conjugated. Look at two UV visible spectra and determine which is more conjugated. And then look at it and see whether or not the results agree. But these are the sorts of things that you need to be able to do for the final exam. Gaussian and UV-Vis, again, all we're looking for is relative conjugation. NMR, be able to calculate coupling constants, chemical shifts, be able to determine integrations if they're not already whole number values. You should be familiar with the regions so that you know which are alkoxy or benzylic, allylic, aromatic, etc., or just plain alkyl as we have down here. You should be able to look at splitting and determine the number of neighbors and determine a structure and determine whether or not that structure does indeed match the structure that you're proposing for a reaction. You should be able to do chemical reactions. If we're given products, be able to determine what the reactants were for a particular type of reaction. Or, if you're given the reactants, be able to predict the product of that reaction. And again, also calculations, the stoichiometry, the common ones, theoretical yield, percent yield, limiting reactant, but also, given GC data, get a crude yield from a crude mixture, and then a crude percent yield from that, but also coupling constants calculation and chemical shift calculations. And that should be it. Hopefully you've been keeping up and learning this along the way, but it'd be a good idea to refresh yourself with that so that you do well on the final exam. Best of luck to you.